Hello everyone. Let's solve another important and frequently asked Gauss's Law exam problem. If we look at the problem, a small charged sphere with mass 1.0 milligrams and charge 2.0 times 10 to the power of negative 8 coulombs is suspended by a string near an infinite uniformly charged sheet. The sphere is in equilibrium, and the string makes an angle of 30 degrees with the vertical. Our goal is to determine the surface charge density, sigma, of the sheet. Before we begin, let's quickly review the key formula. For an infinite charge sheet, E equals sigma divided by 2 epsilon 0. As you can see, the electric field does not depend on the distance from the sheet. That means the field has the same magnitude at every point around the sheet. Now let's solve the problem step by step. Step 1. Analyze the forces acting on the sphere. There are 3 forces acting on the sphere. The weight, mg, acts downward. The electric force, QE, acts horizontally to the right. The reason is that the sheet is positively charged, and the sphere also has a positive charge, so they repel each other. Therefore, the electric force points away from the sheet, which is to the right. The third force is the tension acting along the string. From vertical equilibrium, T cosine theta equals mg. From horizontal equilibrium, T sine theta equals QE. Now divide the second equation by the first. This gives tangent theta equals QE divided by mg. Rearranging the equation, E equals mg tangent theta divided by Q. Step 2. Calculate the surface charge density. Now substitute this expression for E into the equation E equals sigma divided by 2 epsilon 0. Rearranging gives sigma equals 2 epsilon 0 times mg times tangent theta divided by Q. Finally, substitute the given values into the equation. After calculation, we obtain sigma equals approximately 5.0 times 10 to the power of negative 9 coulombs per square meter. Now let's move on to another important and frequently asked Gauss's Law exam problem. Let's solve another important and frequently asked Gauss's Law exam problem. If we look at the problem, we have a uniformly charged solid sphere surrounded by a concentric conducting spherical shell. The solid sphere has a radius A equals 2.00 centimeters and carries a charge Q1 equals positive 5.00 femtocoulombs. The conducting shell has an inner radius B equals 2A, an outer radius C equals 2.4A, and a net charge Q2 equals negative Q1. We are asked to find the electric field at 6 different points. R equals 0, R equals A over 2, R equals A, R equals 1.5A, R equals 2.3A, and R equals 3.5A. Before starting the calculations, let's analyze the different regions and quickly review the key formula. As we know from Gauss's law, the electric field depends on the enclosed charge. For spherical symmetry, we use E equals K times Q enclosed divided by R squared. First step is always asking, how much charge is inside the Gaussian surface? The most important step is always to determine the enclosed charge inside the Gaussian surface. Also remember that inside a uniformly charged solid sphere, the enclosed charge is proportional to the enclosed volume. So we use Q enclosed equals Q times R cubed divided by A cubed. Now let's solve the problem step by step. Step 1. Calculate the field at R equals 0. At the center of the sphere, the Gaussian surface encloses no volume, so the enclosed charge is 0. Therefore, the electric field is 0. Step 2. Calculate the field at R equals A over 2. This point is inside the uniformly charged sphere. So first calculate the enclosed charge using Q enclosed equals Q1 times R cubed divided by A cubed. Since R equals A over 2, the enclosed charge becomes Q1 divided by 8. Now substitute this enclosed charge into E equals K times Q enclosed divided by R squared. After calculation, we obtain E equals approximately 5.62 times 10 to the power of negative 2 newtons per coulomb. In the next part, we'll continue solving the remaining positions and determine the charge distribution on the conducting shell. Now, let's continue with the remaining 4 cases. Step 3. First, consider the point where R equals A, or 2.00 centimeters. This point lies exactly on the surface of the solid sphere. Therefore, the entire charge, Q1, is enclosed by the Gaussian surface. Using the equation E equals KQ1 divided by A squared, we obtain E equals 0.112 newtons per coulomb. Step 4. Now consider R equals 1.5 A, or 3.00 centimeters. If you look at the figure, this point is located between the solid sphere and the conducting shell. The Gaussian surface still encloses only Q1. So we again use E equals KQ1 divided by R squared. Substituting the values gives E equals 0.050 newtons per coulomb. At step 5, we calculate the electric field at R equals 2.30 A, which is inside the conducting shell. Remember an important property of conductors in electrostatic equilibrium. The electric field inside the conducting material is always 0. Why? The solid sphere at the center has a positive charge. This positive charge induces negative charge on the inner surface of the conducting shell to cancel the electric field inside the metal. Since the shell has a total charge equal to minus Q1, there is no charge left for the outer surface. As a result, the electric field everywhere inside the conducting material is 0. Therefore, E equals 0. Now, let's move to the final case. Step 6. Finally, consider R equals 3.5a. This point is outside the entire system. The enclosed charge is Q enclosed equals Q1 plus Q2. Since Q2 equals minus Q1, the total enclosed charge becomes 0. Therefore, E equals KQ enclosed divided by R squared, which gives E equals 0. Excellent! This example clearly shows how Gauss's law allows us to determine the electric field by simply identifying the enclosed charge in each region. Now, let's move on to another important exam type problem. In this example, we have a charged, non-conducting sphere surrounded by a neutral, conducting shell. We need to find the electric field at 4 different positions. Before solving, remember that the first step is always finding the total charge of the uniformly charged sphere. For a sphere with constant volume charge density, we use Q sphere equals rho times the volume of the sphere. After calculation, we get the total charge of the sphere. Now let's solve each part step by step. Part A, R equals 3 centimeters. This point is inside the charged sphere because R is smaller than R. For points inside a uniformly charged sphere, the electric field increases linearly with distance from the center. Using the formula, we get E equals 45.1 newtons per coulomb. Part B, R equals 8 centimeters. Now the point is outside the charged sphere, but before reaching the conducting shell. So the sphere behaves like a point charge, and we use Coulomb's law. The electric field is E equals 29.4 newtons per coulomb. Part C, R equals 12 centimeters. Now we are inside the conducting shell. If you remember, I mentioned this important point in the previous slide and the previous problem. Inside a conductor in electrostatic equilibrium, the electric field is always 0. The charges inside the conductor rearrange themselves on the surfaces, creating a balance that cancels the electric field inside the metal. Therefore, E equals 0. Part D, R equals 20 centimeters. Now the point is outside the entire system. The conducting shell has 0 total charge, so the enclosed charge is only the charge of the inner sphere. Therefore, the system behaves like a point charge with charge Q sphere. Using Coulomb's law, we obtain E equals 4.7 newtons per coulomb. Excellent work. This was another important and common exam problem from Gauss's law. Thank you for following along with this lesson. If you found this video helpful, don't forget to support the channel by liking the video and sharing your feedback in the comments. See you in the next part of the course.